Hi, everybody. My name is Samik, and as you can probably read in the title, we are going to be going over a comprehensive overview of dark matter research. And before we get into dark matter at all, let's start with some introductions. So, again, my name is Samik. I am a senior in California. I go to Bellarmine College Preparatory, and my mentor Jacob and I have been working on this paper for the past few months, and we're really excited to show you well what we have learned as well as what I have learned in particular about dark matter and the whole story of it, more specifically. So why don't we get straight into that? So a brief history about dark matter. So it's important before we even get a chance to really understand what exactly dark matter is, it's important to understand the key figures who sort of paved the way for the discovery of it later on. So on the right, we have Lord Kelvin, as many of you who are within the science community might know. And on the left, maybe a little bit less notable, is Henri Poincaré. And the reason why I bring up these two is because, in fact, Lord Kelvin was one of the first people to actually propose this idea of dark matter. So I believe it was around the 1800s. Lord Kelvin was looking at the stellar velocities of stars and galaxies, and he found something strange, and that was that the stars are moving faster than what he thought they how fast that he thought they would be moving. And the only way he could sort of explain this phenomenon was that there had to be some extra or abundance of unseen mass that pervades within our galaxy, causing the stars to move faster than they should. However, this idea was promptly shot down by Henri Poincaré, which, if you guys might know, is also the, I guess, namesake of something called the Poincaré conjecture. But he essentially said that the observed discrepancy between the experimental velocity, or the velocity that Kelvin observed, and what the theoretical velocity should be was way too small for it to really be considered to any significant degree a new discovery or something else causing these stars to move faster than they would. However, we know that dark matter is sort of a thing in our universe, and about 40, not 40, about 60 years later, we would sort of get the first evidence of that in the form of Fritz Zwicky. A little bit of context on Fritz Zwicky. He was quite to say, well, at least to say the least, quite an eccentric figure. So when he initially proposed that there is this idea of Dunkelmaterie, or dark matter in, I think, French, which is what Poincaré had pointed out, people kind of called him crazy. And the reason why was because when he was looking at this cluster called the Coma cluster right here, he noticed something strange. And that was that stars on the outside of the cluster, of the galactic cluster, are moving much faster than those on the inside, which is strange because if you think about the way how gravity works, the closer you are to the point of gravitational center, the greater to the greater the magnitude of that of the gravity will be felt. But to say the least, the opposite was being experienced here. And so, like Lord Kelvin, Zwicky thought there was also something fishy going on. So he basically stated the same thing Kelvin did, and which is that there is some sort of extra mass, this extra matter that we cannot see that's causing these galaxies, these stars, to move as fast as they are. However, like I mentioned earlier, he was kind of an eccentric figure, and so many of his colleagues didn't necessarily take his words too seriously. And so he was kind of left in the dust when it comes to, paving the way for dark matter discovery, you know, and during that time. However, he's gotten his recognition now, and of course, we wouldn't be talking about him otherwise. So, from Kelvin to Zwicky to now Kent Rubin and Vera Rubin and Kent Ford, these two essentially put Zwicky's theories to the test. And so what they did was that using a um, using a device created by Ford to look at the stellar velocities of stars within the Milky Way, they realized that they realized while observing something called a galaxy rotation curve that what Zwicky said was right. Stars actually at the center of the galaxy were moving slower, or just a little, or much slower than those on the outskirts of the galaxy. And this was kind of like the first big breakthrough for dark matter that actually confirmed that there was something out there. And the reason why it's so significant, I bring up these galaxy rotation curves, is that if, for example, let's say we didn't have dark matter. If we didn't have dark matter and the stars moving just as fast as we see them right now, they would actually be flung out of the galaxy due to the conservation of the law of angular momentum. So for one thing, dark matter is the reason that these stars go around so fast, but it's also the thing that keeps these stars within the galaxy, so that that space is not this jumbled mess of stars that have been flung out from the galaxy. And like I mentioned, this was kind of like the first breakthrough for dark matter. And doing some calculations, they actually figured out that about 85 to 90% of the matter, not things in our universe, specifically the matter in our universe is actually composed of this dark matter that would cause these observations to be perceived. So, what exactly is dark matter? As you can see, I pointed out, I made a similar statistic earlier, but when it comes to sort of examining the entire universe, we believe that dark matter composes about a quarter of what we can actually observe. Well, the vast majority of it is dark energy. And just to make a distinction between the two, dark energy and dark matter aren't necessarily the same exact things. To put it simply, we think of dark energy as the thing that allows our universe to continuously expand. So if you've ever heard of people saying that the universe is constantly expanding faster and faster and faster, it's not necessarily because of dark matter, rather it's because of dark energy. Dark matter, on the other hand, is something that allows us to perceive the structures that we see in our universe the way we do, allows us for the galaxies that we see to actually exist, and on larger scales, in fact, allows something called the cosmic web to exist. But that's a whole other area of reason. Just the bottom line is that dark matter also has a huge role in our universe. So, like I was mentioning earlier, as you can see on the right over here, this is what we sort of see from a galaxy rotation curve. So, on the far right most galaxy is uh, is what we typically observe, and the far and the leftmost galaxy of the same galaxy is what would be observed if there was no dark matter. And you could see just the discrepancy between the two, how you think the velocity significantly drops off with a distance, but it doesn't. It gets faster and faster and faster and keeps consistent for the most part. However, galaxy rotation curves are one thing, and they only explain one aspect of how dark matter interacts with our universe. On the other hand, this is a little bit more of a, I guess, direct observation that requires a little bit less data calculation. So on the left, we have this warped image, as you can see, this warped image of, in fact, a star. And the reason why I point this out is because if we think about Einstein's theory of general relativity, which says that space-time is inherently curved because of gravity, we would think, without it, we would think that we could just see stars the way we do. If I just looked at a star up in the night sky like that, I should see it the way it is. However, because of unseen mass like dark matter, sometimes we have these distortions that causes the light to bend around it, and we get this almost ring-like structure, which is formally actually called an Einstein. Uh, but more importantly, this is evidence of dark matter as well, because dark matter is such a high mass that it allows that light to be bent around it and creates these shapes that we can see using advanced telescope optics. This is another piece of evidence for dark matter, albeit a little bit more advanced. However, on a simple level, the image on the right shows what is called the cosmic microwave background. And to put it simply, it is almost like the echoes of almost like the remnant echoes of the early universe. And the reason why we looked at the cosmic microwave background in the first place is that it actually provides a lot of information about the concentration of dark matter in the early universe. So on the left, we have something called the CMB power spectrum, the cosmic microwave power spectrum. And as you can see, there are these three main peaks that are pointed out. The reason why these peaks are so important is because they are actually matter oscillations. And what I mean by matter oscillations is that as depending on whether it's a compression in the way in the CMB power spectrum wavelength or a rarefaction, the amount of matter significantly contributes to that. So in the flat universe in the first peak, we were basically seeing is this really high peak uh, due to uh, due to the presence of dark matter creating these gravitational wells that allows for it to essentially come out as much more prominent. If we didn't have as much dark matter, we wouldn't see a peak as high. And a similar story goes for the second and third peaks. So a list of potential candidates. Just to go over this briefly, because it seems like a lot of information. To put it short, there are a lot of different possible candidates for dark matter. It's actually quite absurd. I think I've seen more than 20 while doing my research, but usually they fall into one of two camps. Either they're more particle-like, like the WIMP or the macho, or wave-like something called dark photon or an axion. And to put it short, there are so many there's so many different propositions for what dark matter can be, because essentially what happens when scientists are trying to figure out what exactly it is, a new problem arises out of the solution they create, and it's sort of like this constant cycle of solving a problem using this particle or using this wave-like phenomenon, and then getting a new problem out of it. It's just kind of pervasive in this area of study, and that's why we have so many different kinds of dark matter particles, different propositions for dark matter. So moving on to direct detection experiments, just to keep this short, basically, how do you try to detect something that you can't physically interact with or physically can't see? Um, these What we have here are examples of something called the xenon 1T detection experiment. And essentially, what this experiment does is if a dark matter particle hits one of these xenon tubes, it will release a photon and basically scintillate or light up to show that it was in fact hit by a dark matter particle. And this is similar for something called the Super Kamiokande experiment in Japan. And just a little bit more of an interesting figure. These direct detection experiments need to be very deep underground, because there cannot be any interference from cosmic rays or anything from the surface that may impede on dark matter observation. So as you can see, the whole Statue of Liberty, in fact, can actually fit under the Super Kamiokande. And finally, we land on alternative theories, just to keep it brief. So this man right here is Jonathan Oppenheim. And recently he proposed something quite radical, which is that how about we reconcile that space is not in fact simply a classical theory or a quantum theory, basically something that involves waves or something that involves just Einstein's theory of general relativity, but rather sort of a mix of both. And what he calls this is post-quantum gravity. And what he essentially says in this theory of post-quantum gravity is that space has these random fluctuations. And through these random fluctuations, what we be able to see, in at least pertaining to dark matter, is that these observations, like gravitational lensing, these galaxy rotation curves, wouldn't necessarily need to be explained with a dark matter particle or dark matter wave, because we can just attribute it to the random fluctuations in space time. And just to keep it short, funny enough, he took a bet with the professor. I think it was 1 to 3,000 odds that he was right. Um, and we still haven't gotten information about that, but keep your eyes peeled for that. And finally, a little bit more of a controversial take, we have something called MOND, which is essentially modifying Newtonian gravity to account for the for the galaxy rotation curves. And again, just to keep it brief, because there are a lot of things that you are seeing on this page right now, we don't typically go to MOND as a sort of end all be all for dark matter, because it has a lot of flaws. However, recently Northwestern University did a study, and they showed that the galaxy rotation curves predicted by MOND are actually correct. So it's quite an interesting scenario where something that we thought was objectively wrong in our approach for dark matter might actually have some validity to it. So it's something that we shouldn't necessarily toss away. It's something that we still might consider in terms of a possible theory for dark matter. And yeah, that's my presentation. If you guys have any questions, feel free to ask. I'll be here for a few more minutes.
Thank you so much, Samik. What an interesting presentation. It's so super cool that we had two back-to-back astro-related presentations.
Yeah.
While we wait for more Q&A in the chat, I have a quick question. So
Yeah.
I'm curious, what was the most challenging part of your research process with Polygence on this topic?
Uh, so, I mean, there was a lot of things because dark matter is a very broad field, and there are so many different routes that you can take it and go into. But I think the most difficult part was, I think I'd mentioned this thing called the axion in my presentation. That was probably one of the most finicky things for me because the axion isn't necessarily a direct solution to dark matter. It was actually created to solve another problem called the strong CP problem, or the strong CP violation in particle physics. But scientists have found applications for it in in terms of dark matter. And the thing is that you can leave it at that, but it goes down an even deeper rabbit hole, which is that you can find the axion arising in other faraway concepts like string theory. And so I really had to like look into the math and consult that area of expertise to understand what exactly is going on, because these two areas of study were so completely different that I was having trouble trying to sort of figure out where that connection lands.